So picking up where we left off with analyzing graphs of functions, we in the previous video we took a look at some different things involving domain and range. We also did some different things with the vertical line test, as well as how to find the zeros of a function, which are some things we've actually talked about before this. And then we also looked at the concept of how a function increases, decreases, or stays constant as you read it from left to right. So one of the things that we're going to look at in this video here is what's known as relative minimums and relative maximums. So a relative minimum is a point on the graph where the graph changes from decreasing to increasing, and I'll show you an illustration of that in a moment. And then a relative maximum is the opposite. It's the point where a graph goes from increasing to decreasing. So a graph can have multiple relative minimums, a graph can have multiple relative maximums. And I think this diagram right here, this graph, illustrates some different things involving relative minimums and relative maximums. So these 2 points down here, okay, these are the relative minimums. So as you can see with these points, the graph comes in, it's decreasing, and then it hits this point and it begins to increase. Same thing here. As we read it from left to right, the graph is decreasing, and we hit this point here and it begins to increase. So that's a relative minimum. Relative maximums, that's these 2 points up here. And that's the exact opposite effect. So that's the point where the graph is increasing, then it hits this point and it begins to decrease. Same thing here. As we read this from left to right, graph is increasing, hits this point, and begins to decrease. So what we're going to look at graphically speaking is how you do some different things to find relative minimums and relative maximums. So the question up here says, using a graphing utility to approximate the relative minimum of the function. So we're just talking about the relative minimum here, not necessarily the relative maximum. So just remember, when we're talking about graphing utility, okay, the best graphing utility that we have is the graphing calculator. So I'm going to sort of exit out of here. I'm going to pull my calculator up. I'm going to go to y equals, and I'm going to sort of clear this out here, and I'm going to put in 3x squared minus 4x minus 2. And I'm going to graph this. Let me hit zoom 6 here. So once again, I'm just looking for the relative minimums here. So as you can see here, this graph has one relative minimum, and that's this point right down here. So to get your calculator to approximate where that point is, if I go to second and then trace, which is the calculation screen, okay, second and then trace, this is what comes up. So there's a lot of different things that are on the screen that we're going to look at as we kind of move forward, but for what we're talking about now, we're just basically talking about this right here, the relative minimum. So if I go down to 3 or just push 3, okay, I get these questions that come up. So first it says left bound. So if I take this and I kind of approximate where the zero or where the relative minimum is, left bound means I want to pick a point that's what I would say to the left of where the relative minimum is. So I'm just going to pick sort of a point like right out here. The right bound is I want to pick a point that's to the right of where that relative minimum is. So let me kind of bring it back here. And then my guess is where I think the relative minimum is. So I'm going to say it's maybe like right about there. And here's the coordinates of the points you get. So if we're talking fractions, you know, this x coordinate here, this would be positive 2/3. This y coordinate here, this would be negative 3 1/3. So that's the value of the coordinates of this point. The relative minimum, okay, is this y value right here, negative 3 1/3. So that's part A. For part B, I'm going to go back to y equals, and I'm going to put in x cubed plus 5x squared plus x minus 7. So once again, I'm going to graph this. And so I'm just looking for where's the relative minimum here. So as you can see, this graph has a relative minimum down here right pretty close to the y-axis. This also has a relative maximum up here, but in terms of answering the question that's being asked, the question is just asking me for where the relative minimum is. So once again, if I go to second trace and I go to minimum, all right, so I'm going to do the same thing here. For the left bound, I'm going to pick a point that's to the left of the minimum, push enter. The right bound, I'm going to pick a point that seems to be to the right of the minimum. I'm going to push enter again, and then my guess is where I think the minimum is. So it's going to be maybe right about there. And there's the coordinates for the minimum. Okay, negative 0.103, comma, negative 7.051. So that's how you can use your calculator to approximate a relative minimum. So if you take a look at the next part of this, the next example, it says, graph the function below and determine the intervals for which f of x is greater than or equal to 0. So remember that in this particular instance, f of x, okay, f of x is another way of saying y equals this right here. This is really like saying y is greater than or equal to 0. So what I'm looking for here are the values of x that this graph is essentially above the x-axis. Because if y is greater than 0, if you think of your coordinate axis here, okay, it would be all these values up here is where y is greater than 0. So what I want to know is, what are the values for x that give me y coordinates that would be in this area of the graph up here? So once again, I'm going to use, I'm going to graph the function, right? So I'm going to use my calculator to do that. I think that's probably the easiest way to go about this. So let me get rid of this here. I'm going to come back to my calculator. I'm going to go to y equals, and first I'm going to put in 3x minus 1. And I'm going to graph this here. So what I'm looking for here is the position on the x-axis where this graph falls in this area up here. Okay, it falls above the x-axis. So you can see here, this graph hits the x-axis right about here, and then the rest of the graph to positive infinity is above the x-axis. So what I want to really know is what's this value here. So I can use my calculator to do this as well. If I do second trace, and I go to where it says 0, right? Because remember, the 0 of a function, graphically speaking, represents the x-intercept. So if I go to 0, and I'm going to do the same thing here, I'm going to pick a point that's to the left of where the graph crosses the x-axis. I'm going to, for the right bound, I'm going to pick a point to the right of where the graph crosses the x-axis, and then I'm going to pick a point that I think marks pretty close to where the graph hits the x-axis. So here's what I get. X is equal to positive 1/3. So if I come back to this, and I'm talking about an interval now, okay, for part A, the interval for this would be from 1/3 equal to positive infinity. That right there. Okay, because this graph along the x-axis from 1/3 to positive infinity is on the positive side of the y-axis there. And then for part B, let me keep this up here. I'm going to do the same thing. I'm going to come back to my calculator. I'm going to go to y equals, but this time I'm going to put in for part B the square root of x minus 2. And when I graph this, here's the square root graph. So you guys can see here, here's the point where the graph crosses the x-axis, and then from here to positive infinity, okay, the graph is on the positive side of the y-axis. So in terms of figuring out what the value of this point is right here, once again, I'm going to go to second trace, I'm going to go to 0, and I'm going to do the same thing here. So I'm going to pick a point first that's to the left of that 0. Get something that's reasonably close to the 0. So that's here. Then I got the point that's to the right of the 0, maybe right about there. And then my guess is going to be maybe right about there. And the answer to this is x is 4, y is 0. So what that's telling me is this graph crosses the x-axis at positive 4 and then stays above the x-axis all the way to positive infinity. So if we're talking about the answer to this, okay, the answer to this would be the interval from positive 4 to positive infinity. So just notice I'm putting the bracket around the 4 because x does equal 4 in this particular instance here. So finishing up with some different things involving odd and even functions. So one of the things that we've looked at from a few weeks ago is symmetry. Graphs that are symmetric to the x-axis, graphs that are symmetric to the y-axis, graphs that are symmetric to the origin. So when we're talking about some different things involving functions, okay, we have some different symmetry tests that we do that have special names. So the first part of this, a function is said to be even if it is symmetric with respect to the y-axis. The other part of this is a function is said to be odd if it is symmetric with respect to the origin. So here's the thing, there is no name for a function that's symmetric to the x-axis, and the reason for that is because if you had a function that was, or you had a graph that was symmetric to the x-axis, it wouldn't pass the vertical line test. It would not be a function. So that's why we only have even for y-axis, odd for origin. So in terms of trying to keep straight which goes with which here, the thing I always tell people is odd begins with O, origin begins with O. So just something you can use to remember which odd and even goes with which of the two different types of tests. So just remember that the test for even functions, the test to determine if a graph is symmetric to the y-axis, is you take x and you make it negative, and then you resolve the equation in y equals form, and if what you get is the same as the original, then we say that that function is symmetric to the y-axis, which makes it an even function. If we're talking about odd functions, and that's origin symmetry, remember that's make both x and y negative, and resolve the equation in y equals form to see if what you get is the same as the original. So if that ends up occurring, we say that the graph is symmetric with respect to the origin, which makes it an odd function. So just some examples here. You have for part A, g of x equals x cubed minus x. So I'm going to start with making this y equals x cubed minus x. And I'm going to do the even functions first, and then we'll do the origins after the fact. So just remember, even function, right, is symmetric to the y-axis. We want to make x negative when we do that. So I got this here, y equals negative x cubed minus negative x. And when I simplify that, I get this, y equals negative x cubed plus x. So I think you guys can clearly see here, this is not the same as the original, so we would say that this graph is not even. It's not symmetric with respect to the y-axis. But if we're talking about origin symmetry, okay, if I do the same thing here, I got y, I'm going to put this up here, y equals x cubed minus x. So if I make both negative, I got negative y equals negative x cubed minus negative x. So let me deal with this side of the equation first before I deal with the negative in front of the y at the end. So when we did this here, we already got an answer to that, which was what this was here. So I'm just going to kind of put this here. This is negative y equals negative x cubed plus x. And then to put this in y equals form, remember this is a 1 in front of the y, so I'm going to divide everything by negative 1 when I do that. So I get y equals x cubed minus x, which I think you can clearly see here. This is the same as the original, so we'd say that this graph is odd. This graph is symmetric with respect to the origin. So how do you know if you're right? Well, if I take my calculator and just take a look at the graph, so let me go to y equals here, and I'm going to put in x cubed minus x. And if I graph this, I think you can see that the graph is not symmetric with respect to the y-axis, but it is symmetric with respect to the origin. So if you look at your quadrant 3 piece, very similar to your quadrant 1 piece here, and your quadrant 2 piece here, this little hill here, very similar to this piece that's in quadrant 4. So what you're looking at when you're talking about origin symmetry is you're looking at the graph diagonally speaking. So I'm looking at it like this, and I'm also looking at it like this. And are those pieces that are in each of those quadrants, if I flip them over the origin, would they basically be the same piece, which you can clearly see here that it is. So that's part A. Part B, so once again, we'll take care of even first. So if I take y equals x squared plus 1, and I make x negative, this will be y equals negative x squared plus 1. And when I simplify this, I get y equals x squared plus 1, which is the same as the original equation, right? Same as this here. So we would say that this graph is even. It's symmetric with respect to the y-axis. Well, what about odd? So if I take, once again, the original equation, and I put a negative in for y, and I put a negative in for x, right? So once again, let me deal with this side first, right? So I already got that answer from here. So this will be negative y equals x squared plus 1. Then I'm going to divide by negative 1 at the end, and I get y equals negative x squared minus 1, which, as you can see here, is clearly not the same as the original, so this graph is not odd. So once again, how do you know if you're right? Okay, so if I come back to my calculator again, and I put in, go to y equals, and I put in here x squared plus 1. And I just take a look at this graph here. So you get a U shape, which I think you can clearly see here is symmetric to the y-axis. You know, this piece here is the same as this piece over here if I flipped it over the y-axis. But if you're looking at it from an origin standpoint, you know, you have this piece here in quadrant 2, there's nothing in quadrant 4. And then same thing here, you have this piece here in quadrant 1, but there's nothing in quadrant 3. So very clear to see that it's not symmetric to the origin. And then for the last part of this, we have y equals x to the 9th plus 3x to the 5th minus x cubed plus x. I'm going to show you a little shortcut with this last one here. So let's test even first. So I got y equals negative x to the 9th plus 3 times negative x to the 5th minus negative x cubed plus negative x. And when I simplify this, I get y equals negative x to the 9th. This would be minus 3x to the 5th. This would be plus x cubed. And then this would be minus x at the end. So I think you guys can clearly see here that this not the same as the original, so we would say that this graph is not even. But what about odd? So remember that when you're talking about odd functions, you're talking about making x and y negative. So this is what you get when you make x negative. And when you make y negative, all you're really doing is you're taking what's on this side here and you're dividing it by negative 1, which mathematically speaking just takes all the signs and turns them into their opposite. So the shortcut to do, once you've done the test for even functions, the shortcut for an odd function is simply to just take your answer to the even function and just change all the signs. So that's going to make this x to the 9th instead of negative x to the 9th. That's going to make this plus 3x to the 5th. That's going to make this minus x cubed. And that's going to make this plus x at the end, which you can see here, this is the same as the original equation. So we would say that this graph is odd. So just a little shortcut there that you can do once you find your expression for when you make the x's negative, essentially to do the odd test, Just take your answer to the even and just change the signs. So how do you know if you're right? So once again, if I come back to my calculator, I go to y equals, so I'm going to put in here x to the 9th plus 3x to the 5th minus x cubed plus x. And if I graph this, here's what you get. So it's a chair-like shape, sort of like a cubic type shape. And I think you could see here that this graph, okay, not symmetric to the y-axis. If you take this piece and flip it over, okay, there's nothing over here in quadrant 2. And if you take this piece down here, same thing. If you flip it sideways, there's nothing here in quadrant 4. But if you look at this diagonally, this piece here, if I were to flip that over the origin, if I were to flip it diagonally, this is kind of where it would land. So once again, something you can do to kind of check yourself when you get to the end to see if what you have is in fact correct. So that pretty much takes care of all the things that we were going to look at here in regards to analyzing graphs of functions. One of the things that we're going to look at next has to do with some different things with graphs and transformations. What happens, or how do you take a graph and move it up, move it down, move it sideways, move it left, move it right, upside down, that kind of stuff.